Let's now look at some of the properties of the dot product. And as we go with the properties, I want to go through and demonstrate, or if possible, prove these properties so that we know we can trust what we're working with. And the first property is what we just talked about, that there are two ways to compute the dot product, and that allows us to compute the angle between those two vectors u and v. So let's look at the law of cosines. Start with an acute angle just for fun. So I have two vectors, u and v, and we're going to add on to it a vector that creates a triangle. Now, I could draw it either way, but I'm going to draw it coming from the end of v and going to the end of u, and that is described as u minus v, where the positive of the difference is where the two heads meet, and the minus is where the head goes to the tail. So, in a sense, you say, where does it end? U. Where does it begin? V, u minus v. Okay, so that's a way to find the difference of two vectors. You simply create a triangle with them. Now, the law of cosines says that the cosine of the angle between u and v is equal to to get to the cosine of the angle between u and v, we need to start with the law of cosines, which is a generalization or extension of the Pythagorean theorem. So let's describe A as being the magnitude of v, B as being the magnitude of u, and C as being the magnitude of u minus v. Then we have c squared is equal to a squared plus b squared, which is our Pythagorean theorem with the modification, minus 2ab times the cosine of the angle across from the side C. So we substitute what these three components represent. So we have the magnitude of u minus v squared, magnitude of v squared, plus magnitude of u squared, minus 2 times magnitude of u times magnitude of v times the cosine of the angle. Do you see it already? Here we have magnitude of u, magnitude of v, cosine of the angle. Lots of dot product already. So let's work through the other pieces. What about the magnitude of v? Well, that would be v1. Oh, this is an interesting question. What happens if you square a magnitude? Well, that's the same thing as saying the magnitude of v times the magnitude of v. And if two vectors are the same or going in the same direction, the angle is 0. The inner angle is 0, and so the cosine angle is 1. Cosine of 0 degrees. And then Magnitude of u squared is the same thing. Magnitude of u times magnitude of u times the cosine of 0. And then we're subtracting off 2 times the dot product of u and v from our physical notation. And over here we have v dotted with v plus u dotted with u minus 2 u dotted with v. On the other side, we have the difference, u minus v dotted with u minus v. Okay, so that's another way to interpret these squared magnitudes or products of magnitudes. Now, what we want to do is look at the components. And let's stick to just, let's we now want to look at the components of u and v and how they relate to one another. So, this product is going to be a little bit messy because we're subtracting components u1 minus v1, multiplying by u1 minus v1. Let's just write that out. So u1 minus v1 times itself squared plus u2 minus v2 squared plus u3 minus v3 squared. And then the other side, we have the v dotted with v and u dotted with u. So that will give us v1 squared plus v2 squared plus v3 squared plus u1 squared plus u2 squared plus u3 squared minus 2 times the dot product. Now our goal, of course, is to get to the dot product equal to u1 v1 plus u2 v2 and so on. We're starting kind of with this end piece and then working our way back here. So let's move the 2 dot product over to the other side. Get 2 times the dot product equal to, now we'll have these 3 things subtracted from this sum. So let's group like terms together. I have a u1 squared, and then I have a minus u1 minus v1 squared, and then a plus v1 squared. And then we have a similar grouping of u1 squared minus u2 minus v2 squared plus a v2 squared. And then the third set of that, very similar. u3 squared minus a u3 minus v3 squared plus v3 squared. Okay, so that's a lot of terms. How do we know that it breaks down to simple pieces? Let's start with the first grouping. When I expand out this binomial, I will have a u1 squared minus u1 squared minus 2 u1 v1 plus v1 squared. That's all subtracted, plus a v1 squared. From that grouping, we can see that the u1 squareds cancel. We can see that the v1 squared is subtracted, cancelled with the v1 squared is added. And what we're left with is simply a 2 u1 v1. The other groups are the same way. I'll just do one more to demonstrate it. u1 so that's 2 good thing we corrected that, u2 squared minus u2 squared minus 2 u2 v2 plus v2 squared, all subtracted, and then plus a v2 squared on the outside. This will cancel out the u2 squareds, the v2 squared, because that's been subtracted, and we're left with a plus 2 u2 v2. And then the last piece will be the same way, just it's a 2 u3 v3. And all of that is equal to 2 times the dot product. Canceling the 2's, we get u dotted with v is equal to u1 v1 plus u2 v2 plus u3 v3, where 3 is n the dimension of those two vectors. And mathematicians often will end their proofs with some kind of statement of, "Ha, we did it. It is proven." So there we go. We showed that assuming u dotted with v is equal to magnitude of u and magnitude of v cosine of the angle, then u dotted with v is also equal to the sum of the products. And what's interesting is proofs like this often look backwards. We started with one statement, we want to show it's equal to another, and we ended up assuming the second form and proving the first. We can reverse this process, just the algebra doesn't work out quite as naturally. So I want to show you this direction first. So there is the proof in the book that's described as the law cosines proof that shows you the two definitions or computations of the dot product are the same. Whew. Okay, and to wrap it up, we do know that the angle is the cosine inverse of this ratio, and we can write it the division sign because the dot product is a scalar and magnitudes are scalars as well. Okay, so now let's look at some of the other properties. Okay, now after that lengthy law of cosines proof, we have a couple of properties that are much easier to prove. First, two vectors are parallel. That's what these railroad tracks or parallel lines are showing. They're parallel if and only if the dot product is equal to plus or minus times the product of the magnitudes. And that's just because. I'll do it on the side here. If we have the case where u and v, u and v are going the same direction, then u dotted with v equal to the product of u, magnitude of u times the magnitude of v. And case 1. Case 2, if u, or let's say v is going this direction and u is going the opposite direction, then u dotted with v is equal to minus magnitude of u times magnitude of v. Why is that? Well, here the angle is 0 and the cosine of the angle is 1. Here, the angle is 180 degrees, or pi radians, and the cosine of that angle is thus -1. That's where that negative comes in. Now, here's an interesting case. What if u or v was the 0 vector? U dotted with the 0 vector. Well, what does that mean? Well, the 0 vector is simply the vector of all zeros, however big it needs to be. So this would be u1 times 0 plus u2 times 0 plus u3 times 0. Well, that obviously is 0. The dot product of anything and 0 is 0. Well, that's also equal to the magnitude of u times the magnitude of the 0 vector. It's not an angle, it's a 0. Because the magnitude of the 0 vector is 0, the square root of the sum of the squares of the entries, which are all 0. So, the dot product of 0 and any other vector is always equal to the product of the two magnitudes, which means the 0 vector is parallel to all vectors. What? Okay, yes, it is true. Mathematically consistent with the definitions we've worked with. Does it make any sense practically? Not really, but we do need it to be true. We still need it to be true, even though we practically don't really think of working with the 0 vector. The 0 vector is simply the vector we get back to once we undo some operation. We move a block from one place to another, and then we move it back. Well, what is the sum of moving it forward, moving it back? That's the 0 vector. It has to exist. And so whatever we do with all the other vectors, we need to be able to do and think about with the 0 vector. Okay, so there we go. The 0 vector is parallel to all vectors. Even stranger now is, or simpler perhaps in some way, is the definition of perpendicular. U and V are parallel. That's an interesting case. We can draw that pretty straightforward. But U being perpendicular to V is even more interesting and strange. If and only if the dot product of U and V is 0. Scalar. What does that mean? Well, that simply means that if two vectors are perpendicular, here's U, here's your V, your angle is 90 degrees or pi over 2, then the cosine of that angle is 0. That's all this. Cosine of the angle is 0. the dot product is 0. Now, we come to the strange part. We just showed that the dot product of any vector and 0 vector is 0, which means that the 0 vector is not only parallel to all vectors, but is also perpendicular to all vectors. Now, you may think, whoa, that is impossible. And we have to be careful here, because when I talked about two things being parallel, we weren't talking about lines. And lines are where we get the notion of parallel, two parallel lines. These are simply, things that have to do with directions. So when we apply these notions of things that we really normally think of in terms of lines, lines being parallel means they're going in parallel directions, directions that are moving at the same angle in a sense. That leads us towards this definition of the dot product being equal to the plus 1 or minus 1 times the product of the magnitudes. And also, treating lines as perpendicular, 90-degree angle leads us to this definition of the dot product being 0 to tell whether or not the two directions of those lines describe lines that are perpendicular. There's no way we can describe a 90-degree angle between a 0 vector and another vector. There's no way. It doesn't make any sense. So, when we see this 90-degree perpendicular notion, we actually will use the more general term, mathematical term, which is not perpendicular, but orthogonal. And orthogonal simply means the dot product is 0. It so happens to mean perpendicular as long as the vectors are not the 0 vector. Neither one is a 0 vector. But orthogonal is a new term to include the 0 vector where this idea of an angle between two vectors no longer is valid. Now, you may think, well, what about the parallel? Well, we kind of let the parallel one slide and we say it's still parallel. But with perpendicular vectors, we actually move to use a different term, orthogonal. Now, this is key in further mathematical courses because this definition of orthogonality being related to a dot product and not to lines at all is so helpful in defining new things. In set theory, we can describe two sets being orthogonal to one another, vectors being orthogonal regardless of whether we have an angle between them. You may think, what about, there's always an angle. Well, what if we're divided by 0? Okay, so the angle only exists as long as neither of the two vectors has a 0 magnitude, which means neither of the two vectors is a 0 vector itself. Okay, so the angle does not always exist, usually exists. So the 0 vector does create these two corner cases which force us to use different language in how we describe vectors to be not necessarily to be correct, I would say. To be correct in all cases, not drive ourselves into a corner we can't get out. Okay, so that's why we use the word orthogonal.